Hello everyone, welcome to this tutorial on implementing an ASM program to generate a delay for a square waveform. In this particular tutorial again we will be using the Texas Instrument TM4C123G at 6 p.m. as the device, and the software would be Keil Microvision 5. So let me first explain the logic of the program. So as we all know, a square waveform alternates between a logic low and a logic high. So this is logic low and this is a logic high. So in our program what we will be doing is, we will be initializing the values for logic low and logic high in the registers, and for this, for initializing the values, we will be making use of the register R4. So initially if it is logic low, then we will store the value of register R4 with 0x00, and if it is logic high, then register R4 will be having a value 0xFFF. We want it to be, we know that these registers are 32-bit registers, so we will store the value 0xFFF. So each state in this particular square wave will persist for a fixed amount of time, which will be determined by the delay. So we can have a delay of any number. In this particular program, I will consider a delay of 8. That means initially, say if I have assigned the value of register R4 to be equal to 0x00, that means you are in the logic low, so you will be giving a delay of 8, and after that you are going to switch from logic low to logic high, and this logic high will persist for a delay of 8. So this delay count that we are specifying, it can be any value. You can have it as a high value or it can be a low value. So mainly the value of your waveform, that is the logic of your waveform, the level in which it is going to be, will be stored in the register R4, and delay will be the count that we will be assigning, and we will be making use of another two registers, register R5 and register R6. Now these are the intermediate registers that we are going to use just to load the value and store the value as to we want to decrement in one particular register content. So these are used as an intermediate to load the value or for performing any arithmetic operations like subtraction. Okay, so the logic goes like this. We will be making use of mainly the counts delay, that is nothing but corresponding to the delay. I am just specifying the label as counts delay. So this is nothing but the delay count which I have specified as 8. Okay, then you are going to set the value, because you know this square wave, that is an infinite signal, right? So you are going to start initially with, say, a logic low. So I will set the value of register R4 as 0x00, that is the low state, and then I am going to make use of this delay subroutine. So I will make use of a delay. So for this I will make use of a single loop which I will name as, say, delay 1m. Okay, so in this subroutine what is basically happening is that the value of your count is getting decremented. So since it was 8, it will go on decrementing from 8, it goes to 7, then 6, 5, 4, 3, 2, 1. Okay. So, as long as it is going to be decremented and reaching a value equal to 0, the output is going to remain in the low state itself. That means the value of R4 is going to remain in 0x00 itself. So, this delay loop makes sure that the value of your counts delay is getting decremented. Once it is decremented, what happens is that now the value of R4 is switched to 0xFF F. Okay. Since it is 32-bit register, we need to make sure that we are having enough Fs. So, this is nothing but your high state. Now, again what we are doing is, again the delay loop will be called, the delay label which I have given as delay 1m, and the value of my counts delay is 8, right. So, this 8 is going to be decremented as 8, 6, 5, 4, 3, 2, 1, and during the decrementing of this particular delay, the value of R4 is going to remain in the high state itself, that is 0x FFFF. Okay. So, the moment the countdown, that is your delay reaches 0, that is when the switching is occurring. Okay. So, the switching occurs when the value of your delay count, that is delay 1m, the label that we have specified, is going to be equal to 0. And similarly, here delay 1m count, when it was in the high state, when it goes on decrementing and reaches the value of 0, it is going to switch, and now the switching will happen where the value of R4 is now again going to be 0x00. So, this is like an infinite loop that keeps on occurring. Okay. So, in this particular waveform, if you observe in this particular square waveform, the delay is the one which is giving us the frequency. And this frequency can be varied to any value whichever you want to. So, continuously what happens is that the program will run in an infinite loop to maintain the toggling of these two stages, that is 0 to 1, 1 to 0, and so on. So, you get an infinite loop which is nothing but equivalent to generating a square wave, right. So, you are decrementing the delay count from 8 to 1, and the moment it reaches 0, switching is occurring, again you are giving a delay, and the moment the count reaches to 0, again the switching is occurring, again you provide a delay, and this goes on. So, this is the logic of the program. So, why we are using these R5 and R6 is because since we are specifying the counts delay, we need to load these values, right, load the addresses. So, that is why we are making use of these registers as intermediate registers. So, let me go to the program and explain to you how exactly this is being done. Okay. So, if you observe, the if you observe the first line of the code, this is basically your header section, and this part, that is your dot data, it defines the data area in the memory, and data basically indicates the area contains the data. It indicates that the area contains the data. Read only specifies that the data is read only. Next, coming to the counts delay, this is basically your label that you are specifying. So, this DCD corresponds to define constant data. So, this DCD is basically initializing a memory location with a 32-bit value, and here we have assigned the value for this particular label to be 8. So, this value will determine the delay count for the square wave generation, and you can change this, as I told you, this value depending on the required delay duration based on the system clock frequency. Then we have align. This align is basically meant for ensuring that there is a proper alignment of data or code in the memory, and typically it is meant for the word boundary. We know, right, these addresses are all 32-bit addresses, and the content that is stored in the registers is also 32-bit. So, they are typically aligned to the word boundary, that is 32 bits. Then coming to this part of the section, this is the code section. And this area my code, it defines the code area in the memory. Code indicates that this area contains executable instructions. Read only means it is code is read only, meant for reading only. The entry marks, this entry basically it marks the starting point of the execution. And export underscore, there are two underscores here, space underscore underscore main. Basically it is telling you that we are exporting this particular symbol underscore underscore main, making it accessible to external modules or the linker. Next, we are starting the program. So, this is the main code like we write in the C program, that is how it has been initialized here, underscore underscore main. Then you want to generate an infinite loop, right? I told you that we are having a logic low first, then we are having a logic 1, and after a delay we are switching, right? So, the switching occurs when the delay reaches a count of 0, and again we are giving a delay when it is at logic high, and this delay when it becomes equal to 0, again the switching is occurring. So, this is like an infinite loop. So, we are giving a label name as loop, and since we want to start with the logic low, that is why we are storing the value of register R4 as 0x00. Then BL delay, BL stands for branch to loop, okay. So, branch to loop delay 1m, okay. So, delay 1m is the label that we have specified here. So, branch to loop, you are supposed to be moving to this particular loop. So, this is basically procedure. Okay, the name of the procedure that is given as delay 1m procedure. So we are using basically a procedure method in order to write the code for the subroutine, because this is your loop, this is basically your subroutine. So what happens is, once you branch to the loop delay 1m, here you are loading the address of counts delay into R6. Okay, so here you are loading the address of counts delay to R6. Then whatever data is being pointed by R6 has been loaded to R5. So you know that R6 is loaded with the address of counts delay, and counts delay has been assigned with initialized with the value of 8. So basically what's happening in R5 is, we are storing the value of R5 to be equal to 8. Now this line of code is optional. If you want, you can keep it, otherwise also the code is going to be executed perfectly. This is just to empty the value of the contents in R6. So next what happens is, once you are here, once you load the value of R5 to be equal to 8, you are going to go to the D loop, and there you are going to subtract R5 with the value 1 and store the new value in R5. So initially R5 was 8, so R5 now becomes equal to 8 minus 1 is 7, and that value will be stored in R5. BNED loop means branch if not equal to D loop. So again what is happening is, in SUBS, basically you have S there, which is meant for indicating the flag. Okay, so BNE not equal basically is going to check if the value of R5 is equal to 0 or not. If it is not 0, then it is going to move back to the D loop. So now what happens, R5 was initially 7, now again it is going to get decremented, it is going to become 6, and then again it is going to compare with BNE. BNE means branch if it is equal to not equal to 0 or no. Since it is not equal, again you are going to move back to subtraction. Now the value of R5 is going to become 5, again not equal to 0, move to the loop, it's going to become 4, and this way you are going to go on reducing the count of R5 to 2, 1, and the moment if it is equal to 0, you are going to come out of this loop and you are going to end the procedure. That means this entire execution is going to get ended. So once that is done, you are supposed to be coming back to this part of the code. So when you come to this part of the code, what has happened is, your delay has become equal to 0, and now the value of R4 is going to be equal to FFFFF. Okay, so you have moved from a logic low to logic 1. Now next, branch to loop delay 1m. So once again you are going to go to this particular procedure, load R6 with the address of the counts delay, content of R6 will be moved to R5, that means R5 will be loaded with 8. You are going to come back to this particular D loop, subtract R5 with 1, and now again R5 will keep on decrementing. So it becomes 7, it is going to be compared with 0, it's not equal, so again subtract 6, 5, 4, 3, 2 and 0. Once it becomes equal to 0, the entire procedure is ended. You are going to go back to this particular line. So in this particular line it says that branch to loop. So branch to loop means again you are coming to the starting point of this particular loop, that is move R4 with 0 x 0 0. So, here the moment it became equal to 0, you are going to come back to logic 0. Again delay is given, and then once the delay becomes equal to 0, you are going to move back to 1. So, this is like an infinite square wave generation, wherein continuously you can observe that the output is switching from logic low to logic 1, and this counts delay is responsible for giving the delay in this particular program, which can be changed based on your frequency. So, let us go to the execution of the code and see how we can implement this in Keil. And finally, here you can observe at the end. So, let us go to the program. So, here I will create a new project, create new microvision project. I will give a name. I need to make use of TM4C123 GH6PM. Click OK. Make sure that you choose the core and the device is properly selected. After that, expand the target. Click on add new item to group source 1. Now it's an ASM program, so I need to choose ASM. I will give some name, delay, add, and let type the code in the editor window. Now here you need to be very careful. You need to give proper indentation, because otherwise you will get too many errors. Because you know that the labeling and the code should be properly aligned. So I will give proper indentation for that. So as I told you, when executing the code, you need not use this move R6 #00. So I'll just for the explanation purpose, I'll just remove this line of code and let's check whether we get the correct result. So let's click on this and check whether our configuration wizard clock configuration is unticked. It is. So here let me save this and I will debug. So after building the target, you can see that there are no errors or warnings here. So let me go to debug project and options for target 1. I need to go to the device. It's properly selected. In the debug option, I need to make use of simulator. Click on OK, and now let me start with the execution. So mainly what happens here is that we need to observe the content of our register R4. We need to see what address is loaded in R6, and in between we need to check what will be the value of our R5. So only 3 registers have to be observed here: R4, R5 and R6. Okay, so let us do the step in execution. So you can see the address has been loaded into R6 and the count has been loaded into R5. So this R5 is nothing but your counts delay, that whatever value that we have assigned, and this is the address corresponding to that counts delay. So now let us see what is the value of R4. R4 is 0x00. So as I told you, we are going to start with the logic 0, right? So you can observe now the counts delay is getting reduced to 7, 6, 5, 4, 3, 2, 1, and the moment it becomes 0, the next this one would be, see, if you want you can also observe the 0 flag. The moment it becomes 0, if you expand this, your program status registers, you can see 0 flag is set to 1. A 0 flag, when it is set to 1, it indicates that when you were comparing B and E D loop, it has become equal to 0, right? So that is why your 0 flag is set to 1 and the register R5 content is 0, and next step execution, you can see R4 becomes 0 x0 FFFF and R5 is 8, and it goes on decrementing up till it becomes equal to 0, and then again switches the value of R4 to be equal to 0 x000, and this way this is going to be a infinite loop operation which will go on and on.